Hello and welcome to the video. Today we'll be looking at projectile motion, and hopefully by the end of this video you will understand projectile motion. To begin, here is the test subject we're using. It is a ball which has a mass of around 20 grams and a diameter of about 7 centimeters. Now in this video we will be treating the ball as a point mass since it is a small mass at low speed. So we can ignore any aerodynamic effects or other effects which may arise from it being not a single point. So let's go into tracker and let's look at the first motion. So here's tracker, and as always, I'll just let the motion play out first. And as you can see, the ball just drops straight down under the influence of gravity. Now let's go back to the slides and look at the equations of motion for this. So here is the free body diagram for the motion we just looked at, and as you can see there's just an acceleration of g in the negative y direction or downward, and from that we can see acceleration equals g in the y direction. Then by integrating that we get the velocity, which equals g times time plus whatever initial velocity the ball has, and the displacement, which is g times time squared divided by 2 plus the initial velocity times time plus any initial displacement we may have. And as you notice, this is the most general form of this motion, so you can input any initial conditions and these equations apply. In this case, we're looking at the special case where the initial velocity and the initial displacement are 0. And we can disregard the x direction since there is no motion or velocity in that direction. So here is a graph of the y position of the motion we just looked at, and the predicted line is just 9.81 times time, or g times time, and the red line are the numbers that we got from tracker. And as you can see visually, the numbers are very close in terms of slope to the predicted slope of 9.81. And if you look at the legend, there is the equation of the line of best fit, which shows that the slope of the red line is negative 9.8 times x, which is in this case is time. So this gives us a remarkably good fit for the motion. So now let's move on and let's look at a slightly more interesting example. So the second example is the same motion, but this time with a constant horizontal velocity. I'll just let it play out. And as you can see, in this case, there is a parabolic arc to the motion, which should give you an idea of what the equations of motion may look like for the motion. So let's look at those equations. So here's the free body diagram of the example we just looked at. And as you can see, just like last time, the only sort of force in the y direction is the acceleration of gravity. So as you might imagine, in the y direction, all the equations of motion are exactly the same as last time. Where things change are in the x direction, whereas previously in the x direction, both acceleration, velocity, and displacement were all equal to 0. In this case, only acceleration is equal to 0, and velocity is equal to whatever initial velocity we gave the ball. And if we integrate the velocity, we get that the displacement is equal to the initial velocity times time plus whatever initial displacement the ball has. Now again, we're looking at the special case where the initial displacement is 0, but these equations work in any general case you may have where there is no acceleration in the x direction. So just like last time, here is the graph of the vertical velocity of the ball. And as you can see, once again, the data points that we got from tracker are pretty close to what we would predict what happened from our equations. Again, the blue line or the blue dots are just 9.81 times time, and the tracker results are whatever tracker got. And there are some irregularities in the data that arise from maybe the camera shaking a little bit or other little issues like that. But the data is pretty close, and you can see from the equation of the fit line that the slope is negative 9.62, which isn't as close as the previous example, but is still well within the margin of error for an experiment like this. Now, here are the position plots for the two examples that we looked. So the blue line is the example with no horizontal velocity, and the red line is the example with the constant horizontal velocity. And this is their y position. And again, notice how close they are. There is some discrepancy, some difference in their positions, but again, this is within the margin of error, and it can result from the ball accidentally having some initial velocity in the y direction, but they're really close, and in an ideal situation they would be exactly the same. And that is everything for this video. I hope you understand projectile motion better after watching this, and have a great day. Goodbye.